optimization of topological features for machine learning applications, presented by Francis Motta and co-authored by Chris Tralie.
Thank you guys so much. Thanks for organizing this. Thanks to everybody for coming. Thanks to my co-author Chris for being here. Thanks also to all of the folks who contributed to this work in some way or another. You'll see there our huge number of authors I've listed up here. At the end, I'll give attributions to each one of these folks. I wanted to just mention that as part of the program in which this work was developed, funded, the DARPA Synergistic Discovery and Design Program, we've adopted the Kasari credit taxonomy. So all of these folks had their hands at some point in the data, generation, curation, manipulation, some of the analysis in some way or another, or supporting the infrastructure in which the analysis was performed, and so they all deserve credit. So thanks to them. Okay, so previous presentation talked a little bit about doing hyperparameter optimization. My whole talk is going to be about hyperparameter optimization of both learning models and of feature generation, topological feature generation, simultaneously. Okay, so to get started, I'm going to be applying these techniques that were developed in the context of this program to two data sets, one of which comes from a challenge problem within this DARPA program. So I'm going to be sharing with you some very interesting data, and I'd like to introduce it now and kind of give you the context of the problem that we're working in. So in 2017, members of the Baker Lab at the University of Washington, led by Gabe Rocklin, came up with this assay, or published the results of this assay, that enables them to quantify protein stability in a high throughput manner. So the details of this assay are sort of given by this cartoon. I'm not going to go into that too much, but the big takeaway is that we're able to assay protein stability for synthetic proteins on the order of 30 to 50 amino acids that are designed by the Baker Lab and people therein, measuring, or they quantify sort of how stably these proteins fold into a stable conformation, or minimal energy conformation. And they can do that on the order of thousands or tens of thousands of proteins simultaneously. So the outputs of these assays are huge data sets that characterize protein stability across tens of thousands of proteins. And what this has enabled researchers to do is to start developing machine learning models that can predict protein stability from biophysical characteristics. So far the work that was in the science paper that motivated all of this work and the challenge problem that I'm going to be talking about, they applied linear and logistic regression models to large collections of biophysical characteristics of these proteins that were estimated by a software platform called Rosetta. And these biophysical characteristics are kind of hand curated. They're features of proteins that subject matter experts understand are associated with protein stability. Things like hydrophobicity, having nonpolar cores in the protein in the tertiary structure. Okay, so these are some characteristics which can be quantified and measured and then used to actually train a machine learning model on. Okay, so this assay has enabled this kind of a training, or this kind of a supervised learning problem for predicting protein stability. So that's one of the data sets. Part of the Synergistic Discovery and Design program is about developing generalizable methods that can be applied broadly across different problems. And so as part of work for this paper and for this publication or for this conference, I kind of handed off the tools that were developed in the context of this challenge problem to Chris Tralie, collaborator, who had access to a related problem, a supervised learning problem, but in a totally different data set. This is 3D micro CT surface reconstructions of certain tissues in human bones, where shape-based features are important at characterizing the strength or the other kinds of structure or other kinds of medically relevant measures inside the bones. Okay, so one of the accepted features in this context is called the trabecular number. So just to give you the specifics of what that is, it's the inverse of the average distance between branches of the medial axis of the shape. So shapes with large holes tend to have lower trabecular number. And so the particular problem that we're interested here is not in predicting protein stability, but it's predicting this number, this trabecular number that's associated with medically relevant measures, such as bone strength. Okay, so again, I mean, both of these problems are kind of the same in that they sort of follow a topological data analysis to machine learning pipeline, where our interest is in trying to apply persistent homology in particular to extract shape-based features from each one of the samples, which could be, tens of thousands of samples in the case of the protein design, and extract those features, turn them into features that then can be plugged into a machine learning algorithm in order to perform classification, perform regression, prediction, etc. So that pipeline has seen a lot of attention lately from researchers, in particular on the step of transforming the output of persistent homology calculation into a representation that's amenable to machine learning methods as they exist today, or as they've been popularized, and they've seen a lot of success. So these are sort of vectorizations of persistence diagrams and converting persistence diagrams into finite dimensional or infinite dimensional vector representations, giving this topological encoding more structure that can be leveraged by machine learning models to train on. Okay, so here is a list of some of the more popular ones that have been seen in the literature to be successful in various applications. If your favorite one is not up there, sorry, please complain to me at some later date, and I'll be happy to add your favorite method up there, because there's many different approaches to this. And that's kind of the point of this talk, is that when you're given a problem or you have a particular application in mind, it may fit into this kind of a pipeline where you think, I can generate novel features that are topological descriptors of shape, using persistent homology, for example. And I have a supervised learning problem that I want to try to train a classifier or regression on, and that's great. But which method should I use? What's going to work? We have all these options, and along with all of these options are other kinds of hyperparameters as well. So the first observation is that I regard each one of these choices as sort of a model choice and as a hyperparameter in its own right. And if I zoom in on, this isn't just a shameless plug, but this is also just to highlight the fact that if you pick a particular method of vectorization, that depending on which one you choose, it may also have other hyperparameters that you have to specify. Okay, that you have to choose in order to actually develop the model. So in particular, persistence images, this is a method that's seen some attention in applications, and it requires one to choose a number of hyperparameters. In the original paper, we sort of showed that, at least for the applications we were looking at, the choice of hyperparameters didn't matter too much into the overall model performance. I guarantee that that's not always going to be the case, okay? And that, in fact, choices of hyperparameters that specify the particular encoding of your persistent homology information into a finite dimensional vector will affect model performance. And so, how do you choose those? Okay, how do you choose those hyperparameters? Well, in the supervised learning world, or in machine learning in this community, it's already well known, well accepted that models come with hyperparameters. Right? This is something that people accept. And so a lot of attention has been given to developing smart ways of optimizing over hyperparameter space. And finding optimal choices of hyperparameters, because it's known that you can get significant boosts in model performance by just tuning the way that your model is trained. So I want to focus briefly on just a couple of examples. I'm not actually going to show any neural networks results. All the models I'm going to use today are either linear regression models or random forest models. There's a reason for that. It's not important. Certainly one could apply neural networks to the kind of data I'm going to output here and show you. Anyways, the particular hyperparameter that I'm interested in for decision trees is minimum samples per leaf. So that's going to be an important hyperparameter in some of the results I'll discuss. This kind of controls model complexity, right? So as you're building a decision tree, let's say you have a bunch of samples in some Euclidean space, represent some feature space. You're slicing up building a tree by slicing up this Euclidean space into into regions, and if you only insist that you have a single sample in every leaf node of this tree, you can have an extremely overfit model, a very complex model that doesn't generalize at all, and so you can tune this particular parameter to kind of control your model complexity and thus overfitting. But there's lots of these, right? You look at any of these models and there comes with huge numbers of hyperparameters. We make very complex parameter spaces that are difficult to optimize over. So some uninformed methods were mentioned: grid search, random search, but there's some informed methods. And in particular, I'm going to be focusing on Bayesian optimization techniques for dealing with the kinds of parameter spaces or configuration spaces that emerge from this TDA machine learning pipeline very naturally.
5 minutes.
5 minutes, okay. Great, so here we are, TDA machine learning pipeline. Again, a couple of different examples of the vectorization step. Naive vectorization, just sorting your persistence pairs and then concatenating the coordinates that appear in your persistence diagrams. As one way of vectorizing, that's been applied in a couple of different contexts, and then persistence images, which I showed before. But there's also then the machine learning step, right? The actual learning model that comes with its own hyperparameters. So there's hyperparameter optimization happening at the feature generation step, or required or needed at the at the feature generation step, and also at the training step. And this leads to these configuration spaces, which are conditional and awkward, right? They have different types of underlying parameter structures, right? You have continuous parameters, you have discrete parameters. You have, if you view your model or your vectorization approach as a hyperparameter of its own right, then you have conditional parameter spaces. Yeah, it depends on the actual parameters. The hyperparameters of persistence images are different from the hyperparameters of choosing concatenation of top persistence pairs. And so this gives a sort of tree-like structure that we need to be able to deal with. And there's been some recent work on this, a very nice package called HyperOpt that was that's freely available here on GitHub. And here's the reference to the underlying work that describes its appropriateness for this kind of configuration space, these tree-based configuration spaces, awkward parameter spaces. Okay, so let me very quickly just go through the big takeaways from our experimentation using those two data sets that I talked about at the beginning. So first of all, Bayesian optimization is well suited to this kind of a problem. We see that it explores, and it does so in a smart way, right? It reduces the difficulty of the problem of evaluating these objective functions, in this case, like your model performance, which requires initially a vectorization step and then a training step, which combined can be extremely expensive. So it minimizes the amount of actual times you have to do this process because it explores regions that are top performing. So you can see here that I'm illustrating here a grid search over all of the start persistence pair to end persistence pair hyperparameters. Hyperparameter choices one could use in order to try to do a classification of proteins into stable or unstable. And you can see here that this Bayesian optimization technique focuses on those regions which are most likely to be successful, and over a few trials we get very close to the absolute maximum performance of our model. Another big takeaway. This seems obvious, but it's nice to see an example of it. The vectorization parameters depends on the homological dimension. So if you're going to be using loop structures and void structures or higher dimensional analogs from the persistence calculation in order to generate topological features, you shouldn't use the same vectorization parameters for both of these. It's unlikely that they're, well, maybe not unlikely, but in this case it shows that it can depend on the homological dimension. Another interesting takeaway is that there is an interaction between the learning model parameters and the vector generation parameters. Okay, you shouldn't expect that you can generate vectorization that's going to work across all different choices of model parameters. You shouldn't optimize these things separately. They need to be optimized simultaneously. So this illustrates that. Here I'm using a random forest regressor to predict the actual protein stability score that comes out of the Rockland assay, and fixing the minimum samples per leaf parameter across a range of different values. And you can see this sort of the way that impacts the region of optimal performance in the persistence image parameter part of the parameter space. And it varies pretty dramatically and in a sort of counterintuitive way, a way you wouldn't actually expect. I won't, given time, I won't say too much more about that.
One more minute.
Okay, yeah. So same kind of conclusion is drawn from these figures, right? This is now for ridge regression, where our measure of model performance is leave one patient out cross validation. So we train on a set of patients and then we test on the patient that it's never seen before. And what we can see again is that the regularization parameter in the ridge regression model that influences the optimal choice of parameters for the persistence image vectorization in a way that's actually kind of consistent with our intuition, in a sense that the regularization parameter of this model is sort of, the kernel size, the kernel bandwidth in the persistence image vectorization, and the pixel size can sort of act as a regularization parameter and do so in a way we expect. Okay, so what else? Oh, this is this bottom plot is quite interesting. What this shows is it shows error curves varying over model regularization parameter. So that's this plot here. Okay, model regularization parameter here for two different choices of fine or coarse vectorizations. So very high dimensional and very low dimensional vector representations of these persistence diagrams. And what you can see is that the optimal choice of regularization parameter shifts depending on if you're using coarse or fine values, but the resulting weights of the ridge regression models are basically just super resolutions of each other, right? So this is just, you see almost identical weights, but just increasing the resolution along with the persistence image, which may or may not be surprising to you. It was somewhat surprising to us when we first saw it. However, if you were to fix if you were to optimize first for a coarse choice of vectorization, the value beta 1, the optimal regularization parameter there, instead evaluate that at fine vectorization at that choice of regularization parameter, you get a much worse model performance overall, and you get very, very different weights appearing in the ridge regression model. And so again, simultaneous optimization of both model and vectorization, crucial. So here are all of my co-authors and their contributions. Again, credit taxonomy. Thank you so much.
Thank you. So let's take one question. We don't stop during the break, so we have a coffee break after this. But if someone has one question that they would like to ask.
Yeah, so thank you very much. I actually sympathize a lot with the effort here, as I'm working in a similar kind of project, very interesting. And so one question I have is there's kind of recent developments in the PA community. Name one kind of that's come up recently called Tralie, right? So these are kind of techniques that try to go along the direction of automatic feature learning in the spirit of neural networks, right? And sort of the question is effectively this here we're talking about hand-generated features, right? Could be because of images or silhouettes or whatnot, and something else that we're working on a lot. But now I wonder, are we about to enter an era when this is superseded by automatic feature generation in the style of neural networks, or is there still plenty of scope for this to have the same?
Sure. Well, on the one hand, I think this is one step away from manual generation of features, right? In the sense that we're doing. You could imagine this being incorporated into an automatic learning pipeline where you're doing hyperparameter optimization automatically, so you never had to make choices about those things. On the other hand, I agree with you. There are methods, and in fact, the next speaker, is it you? No? Okay. The next speaker is going to talk about data-driven feature selection, like CEDAR, the CEDAR model. And I'm less familiar with this neural network approach to generating features, but I think it's in the same vein, where, you can automatically generate features that in a data-driven way without having to, choose these hyperparameters necessarily. I would say that, maybe it will be. It will be superseded by those techniques, and there's a lot of advantages to not having to tune hyperparameters. if you can do so in a much more data-driven way, like Cedar, as you're about to describe.
All right.
Yeah.
Thank you very much.
Would be great descending, takes you faster to an optimum than a research.
Yes.
Thank you very much.
Absolutely.
All right, so we have